universal force like gravity that varies inversely with the square of the distance, but which is billions upon billions times stronger. If there were such a force, and if it were attractive like gravity, the universe with all its matter would be pulled together into a tight ball. Yuck, not good. But suppose this force were a repelling force, where every particle repelled every other particle. What then? The universe would be an ever-expanding gaseous cloud. Again, not good. But let's suppose that the universe were composed of both attractive and repulsive forces. Suppose the root of these forces were particles, say, positives and negatives. Further suppose that the positives repel positives and negatives repel negatives, but attract positives. Like kinds repel and unlike kinds attract. And what if there were equal numbers of each? What would the universe be like? The answer is simple. It would be like the one we're living in. Well, there is such a force. We call it the electric force. Yum. The electric force between things balances out because of equal numbers of positives and negatives. All things around us attract one another electrically, but repel one another just as much. That's why the enormously strong electric forces between Earth and Moon have been balanced out. This is why the much weaker gravitational force, which only attracts, is the dominant force between these two bodies, and the dominant force in the universe. It's a gravitational force that holds the Moon in orbit. Similarly, it's the electric force that holds electrons in orbit about atomic nuclei. For example, in a hydrogen atom, the proton that makes up the nucleus holds an electron in orbit. Charges with opposite signs attract. The fundamental rule of electricity is that like charges repel one another, unlike charges attract. Protons are positively charged and electrons are negatively charged. The attractive force between protons and electrons holds atoms together. A study of chemistry finds various ways that atoms bond to form molecules. Beneath all these bondings are electric forces, all of them. And that's why anybody studying chemistry has to know something about electricity. Getting back to the electric force. As strong as it is, it weakens with distance. Like gravity, electric force is an inverse square force. It decreases inversely as the square of the distance between charges. This was discovered in the 18th century by French scientist Charles Coulomb and is called Coulombs Law. Coulomb's law tells us that for charged objects much smaller than the distance between them, ideally particles with point charges, the electric force varies directly as the product of the charges and inversely as the square of the distance of separation. In this equation, Q sub 1 represents the quantity of charge on one particle, and Q sub 2, the quantity of charge on a second particle, and D, the distance between them. This force is along a straight line from one charged particle to the other. Notice how similar this is to Newton's law of gravity. Recall that when we divide gravitational force F by the quantity m1, m2 divided by distance squared, that we get G, the universal gravitational constant. Then the proportion can be written as the exact equation. Force equals G times m1 and m2 divided by distance squared. Similarly, when we divide the electric force F by the quantity Q sub 1, Q sub 2 divided by distance squared, we get a constant, which we call K. Then we write Coulomb's law as the exact equation. F equals K times Q sub 1, Q sub 2 divided by D squared. The major difference between these two kinds of force is that gravity only attracts, while electric forces may either attract or repel. Significant difference. Using the equations for Coulomb's law to guide our thinking, we can answer questions such as, what happens to the force between a pair of charged particles when one of the charges is doubled? Can you see that the force is then doubled? Or, instead of doubling one charge, suppose we triple the charge in one of the particles. We see that the force between the particles is tripled. Can you do big numbers? Suppose we increase the charge of one of the particles by 100. How would the force change? By 100. Not surprisingly. Or instead of increasing charge, how about increasing distance? Suppose we double the separation distance. Now d becomes 2d, but distance is squared. So we see that we get 4d squared. And can you see this makes the force between the particles 1/4 as much? I hope so. I want to leave you with a question. If instead of doubling the distance between a pair of charged particles, suppose we halve the distance, that is, bring them closer to half the distance, how will this affect the electric force between them? You got it? That's it for now.